For our senior design project, we worked with the Greater Pittsburgh Community Food Bank to help model their distribution capabilities. The team group members were Alex Fetterman, Andrew Meyer, and Stephen Rose. The Greater Pittsburgh Community Food Bank is a nonprofit organization located in Duquesne, Pennsylvania. Their goal is to eliminate hunger in southwestern PA. They currently serve 23 million meals per year to clients, agencies, and partner distribution organizations, or PDOs. Here's a sample model of the food flow from the food bank to the clients. As you can see, the food bank delivers to PDOs, agencies, and clients, while the PDOs deliver to agents and then ultimately to the clients. In order to adequately feed the greater Pittsburgh area, the GPCFB plans on doubling the amount of meals they serve. They also want 50% of the food they distribute to be produce. As of right now, they have no idea how these changes will affect their trucking fleet.
Our proposed solution to solve this problem was to develop an Excel model that simulates their distribution over the next 10 years and accounts for the increases in demand. The model will be capable of testing a variety of scenarios, such as continuing operations as normal, separating the produce and non-perishable delivery routes, and increasing the frequency of deliveries to account for weekly, bi-weekly, and monthly shipments. The model will utilize two major constraints: the capacities of each truck and the time required for routes.
The first step in completing our project was to research the distribution tactics and methods employed by the food bank. By acquiring this background information, we were then able to determine what factors would affect the system and our model. From there, we collected and analyzed data relating to those key factors, such as the trucking capacities, route distance, and stops per route. We then constructed a linear programming model that could be used to simulate a variety of scenarios based on user inputs. We were able to get an understanding of the system through meetings with senior management and warehouse operators, and through reviewing the methods used in their forecasting model from the previous semester's project. Once we had this information, we took the opportunity to shadow an actual route, where we were able to observe how routes are created the day before, and also how they are executed. This allowed us to visualize the constraints that we had determined through our meetings previously. All the data relating to demand we were able to gather from the forecasting model produced in the previous semester. Here's a snapshot of that model. This shows you the breakdown of demand by county and by program for the year 2016. The majority of the information relating to the trucking fleet and to the routes themselves was handwritten and needed to be processed into an Excel spreadsheet to be usable in our data analysis. For example, here, you can see one of the trucking logs used by a driver to detail where they were going, what time they arrived, what time they left, how many miles they had driven, and what was the nature of their stop.
After extracting the data from the driver logs, we input it all into Minitab to find appropriate distributions. We found that the data for the unloading time per pallet, the number of pallets delivered per route, and the total miles per route were best represented with a long normal distribution. The time taken at each pickup location followed a gamma distribution, while the driving time per mile followed a normal distribution. The remaining datasets had to be fit with an empirical distribution for use in our simulation. These distributions were then used to generate our random samples within the model. To create our Excel model, we considered two main constraints: the physical capacity that each truck could handle and the number of work hours available. The first constraint, the capacity of the trucks, was dealt with fairly simply. Our model converts the demand data into number of pallets, which must be less than or equal to the total number of pallets that can be handled by the trucking fleet. The time constraint was dealt with in a much different way. Using the time-related distributions that we generated, we simulated a full day of routes for the entire fleet. From this, we were able to compare the number of simulated work hours necessary against the number of actual hours available. The model then uses linear programming and Excel's solver tool to minimize the number of trucks needed while sufficiently servicing all of the demand and meeting these two major constraints.
This is a portion of our inputs page from the model. Anything that is highlighted in orange can be changed by the user. For example, they can adjust the model for seasonality based on year, month, week, or day, and they can also change their current fleet in operation and how efficiently they're packing it, among other things. There is also a separate section of the inputs page that can be used for the potential split produce and non-perishables model. When the user is satisfied with the inputs, they will run our Excel solver. This solver will determine what the optimal fleet is based off of both the trucking capacities and off of the time and distance component. It will then provide a readout of this for the user so they can see how many of each size truck they should need.
Along with our Excel model, our team generated 3 recommendations for the food bank. The first is to implement a drop-and-go location in both Somerset County and Lawrence County. A drop-and-go is essentially a single large drop-off point that many smaller member agencies can visit to retrieve their desired shipments. This will consolidate the number of drop-off points in these 2 regions and minimize the number of long-distance trucking routes needed. The second and third recommendation both relate to the acquisition of new trucks throughout the next 10 years. Using our Excel model, we concluded that 8 trucks and 1 tractor-trailer will need to be purchased by year 2025 to keep up with the rising demand. Therefore, a total of $985,000 should be budgeted out for the purchasing of new trucks under the 10-year strategic plan. Collaborating with the food bank team has been an amazing experience, and we have thoroughly enjoyed working on this project with them. We would especially like to thank Don Ziegler, our project sponsor, along with Justin Lee, Ed Marco, Tom Zambo, and the entire GPCFB team. We would also like to thank Pitt faculty members Dr. Hoda Bakori and Dr. Jayant Raj Gopal for the contributions in making this project a success.